A kite 100 feet above ground moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string has been let out? So again, we want to have a diagram. So here we are, we've got our person, and we've got the kite, and then the string is the hypotenuse of this triangle. And let's see, what can we label? A kite 100 feet above the ground moves horizontally. So we know the height of the kite is always going to be 100. And because it's moving, we don't know what the base of that triangle is, what that horizontal distance is, so we can let that be x. And then for our third unknown, the length of the string at any given moment, we'll call that y. We could call it d for distance, but I don't like the derivative being dd over dt. It's a little bit nicer when it's dy over dt. So let's let that be y. And we are specifically interested in the angle between the string and the horizontal. So that's the angle near our person. I'm going to call that angle theta. And so we want to know the relationship between theta and, let's see, we know that it's moving horizontally at a speed of 8 feet per second. So we know the rate of change of x, and we want the rate of change of theta. So we need a relationship for x and theta. We don't want to include y, because then we would also need the rate of change of y. So we want a relationship with theta x and 100, and it looks like that's going to be either tangent or cotangent. We could say tangent theta equals 100 over x, or we could say cotangent theta equals x over 100. Using tangent has the advantage of the fact that you might be a little bit more likely to remember the derivative of tangent than cotangent. I feel like we see tangent more. The disadvantage is that the variable's in the denominator. On the other one, with cotangent, the advantage is that the variable's in the numerator, so it's slightly easier derivative to take, but we might not remember the derivative of cotangent. I am going to use cotangent because I think it's good to get practice with that, but I encourage you to try the problem again with tangent and make sure that you get the same answer. So when we take cotangent of theta equals x over 100, and we differentiate that with respect to time, on the left-hand side, we have to differentiate cotangent, and the derivative of cotangent of theta is negative cosecant squared of theta. But then we have to multiply by d theta over dt, because we've got to use the chain rule. Theta is a function of t, of time. And on the right-hand side, we have to differentiate x over 100. That is going to be 1 over 100 times dx over dt. Now, we need to start plugging things in. We're going to need to know cosecant of theta. Remember, cosecant of theta is just 1 over sine of theta. Sine of theta is opposite over hypotenuse. Now, we need to know the value of y at that moment, but remember, at this moment, we're told 200 feet of string has been let out. So that means y is 200. So at this moment, sine is 100 over 200, which is 1/2. And that means cosecant is the reciprocal of that, which is just 2. So this is going to be negative 2 squared times, well, d theta over dt is the quantity we're trying to get. And then on the right, 1/100th times dx over dt. But we're told that the rate of change of x is 8 feet per second, so that's going to be 8. Let's see. So if we want to get d theta over dt alone, we're going to have to divide by negative 4, because that's what negative 2 squared is, or the opposite of 2 squared. And so that's going to give us d theta over dt equals 8 over 100 times -4 is -400. And we can reduce the top and bottom by 8. When we do that, that gives us -1/50th. And this is a rate of change of an angle. And so it's going to be radians per second. And so we're asked to find at what rate is the angle between the string and horizontal decreasing. So we know the rate of change is -1/50th. That means it is decreasing at a rate of 1/50th radian per second.